Banach manifold. In mathematics, a Banach manifold is a manifold modeled on Banach spaces. Thus, it is a topological space in which each point has a neighborhood homeomorphic to an open set in a Banach space. A more involved and formal definition is given below. Banach manifolds are one possibility of extending manifolds to infinite dimensions. A further generalization is to Fréchet manifolds, replacing Banach spaces by Fréchet spaces. On the other hand, a Hilbert manifold is a special case of a Banach manifold in which the manifold is locally modeled on Hilbert spaces. Definition: let X be a set. An atlas of class CR, R equals 0, on X is a collection of pairs called charts UI phi I such that each UI is a subset of X and the union of the UI is the whole of X. Each phi is a bijection from UI onto an open subset phi UI of some Banach space I, and for any I and j phi UI, UJ is open in I. The crossover map PH J PH I 1 PH I U I U J PH J U I U J display style varphi j circ varphi I1 varphi IUI cap UJ to varphi JUI cap UJ is an R times continuously differentiable function for every I and j in I, i.e. the RTH Fréchet derivative. D R PH J PH I 1 PH I U I U J LIN E I R E J display style mathem dr big varphi j circ varphi I1 big varphi IUI cap UJ to mathem lin big EIR EJ big exists and is a continuous function with respect to the I norm topology on subsets of I and the operator norm topology on linear edge. One can then show that there is a unique topology on X such that each UI is open and each phi is a homeomorphism. Very often, this topological space is assumed to be a Hausdorff space, but this is not necessary from the point of view of the formal definition. If all the Banach spaces I are equal to the same space E, the atlas is called an E-atlas. However, it is not a priori necessary that the Banach spaces I be the same space, or even isomorphic as topological vector spaces. However, if two charts UI phi and UJ PHJ are such that UI and UJ have a non-empty intersection, a quick examination of the derivative of the crossover map PH J PH I 1 PH I U I U J PH J U I U J display style varphi j circ varphi I1 varphi IUI cap UJ to varphi JUI cap UJ shows that I and edge must indeed be isomorphic as topological vector spaces. Furthermore, the set of points X for which there is a chart UI phi with X in UI and I isomorphic to a given Banach space E is both open and closed. Hence, one can without loss of generality assume that, on each connected component of X, the atlas is an E-atlas for some fixed E. A new chart U PH is called compatible with a given atlas UI phi I if the crossover map PH I PH 1 PH U U, I, PH, I, U, U, I, backslash display style backslash varphi I backslash circ backslash varphi 1 backslash varphi U backslash cap UI backslash to backslash varphi IU backslash cap UI is an R times continuously differentiable function for every I. I2 atlases are called compatible if every chart in one is compatible with the other atlas. Compatibility defines an equivalence relation on the class of all possible atlases on X. A CR manifold structure on X is then defined to be a choice of equivalence class of atlases on X of class CR. If all the Banach spaces I are isomorphic as topological vector spaces, which is guaranteed to be the case if X is connected, then an equivalent atlas can be found for which they are all equal to some Banach space E. X is then called an E manifold, or one says that X is modeled on E. Examples: if X is a Banach space, then X is a Banach manifold with an atlas containing a single, globally defined chart, the identity map. Similarly, if U is an open subset of some Banach space, then U is a Banach manifold. See the classification theorem below. Classification up to homeomorphism. It is by no means true that a finite-dimensional manifold of dimension n is globally homeomorphic to Rn, or even an open subset of Rn. However, in an infinite-dimensional setting, it is possible to classify well-behaved Banach manifolds up to homeomorphism quite nicely. 1969 theorem of David Henderson states that every infinite-dimensional, separable, metric Banach manifold X can be embedded as an open subset of the infinite-dimensional, separable Hilbert space H up to linear isomorphism. There is only one such space, usually identified with L2 backslash display style backslash L2. In fact, Henderson's result is stronger. The same conclusion holds for any metric manifold modeled on a separable infinite-dimensional Fréchet space. The embedding homeomorphism can be used as a global chart for X. Thus, in the infinite-dimensional, separable, metric case, the only Banach manifolds are the open subsets of Hilbert space.